we present Mass Spiking Transformer, a new architecture that applies the self-attention mechanism using ANN to SNN conversion to achieve high-performance spiking neural networks. A random spike masking method is introduced to prune redundant synaptic operations for energy savings. Spiking neural networks are computing models inspired by the brain that communicate via binary events called spikes, rather than just activation levels. The neurons in SNNs generate spikes at each time when their accumulated membrane potential exceeds a threshold, otherwise, remain inactive. The use of binary time series data in SNNs, as opposed to the continuous data representations in conventional networks, reduces data redundancy and lightens the processing load. While SNNs provide notable energy efficiency gains on neuromorphic hardware, there still remains a considerable challenge to achieving performance comparable to artificial neural networks in real-world applications. Besides, the mainstream method for ANN to SNN conversion trade increased simulation time and power for high-performance SNN, and generally consumes lots of computational resources when making inference. We propose an energy-efficient architecture, the Mass Spiking Transformer, that combines the benefits of SNNs and the high-performance self-attention mechanism in Transformer utilizing the ANN to SNN conversion methods. Besides, our method, called random spike masking, prunes input spikes during both training and inference to reduce SNN computational costs. We use the SWIN transformer as the backbone network, replacing all layer normalization with batch normalization to resolve mismatches between ANNs and SNNs. The masking rate specifies the probability of transforming an input spike into a failed state, pruning redundant spikes and inhibiting neuron communication. For example, here, the actual transmitted value is determined by the raw input and mask value. Our work evaluates the impact of applying random spike masking in the self-attention and MLP modules across various model architecture. When converting ANNs to SNNs, clipping, flooring, and unevenness errors occur. The masked spiking transformer with layer normalization causes severe distribution mismatch. We resolve this problem by replacing all the layer normalization layers with batch normalization layers to preserve distributions, enabling stable conversion. Our masked spiking transformer combines the self-attention mechanism and the ANN to SNN conversion method, achieving state-of-the-art accuracy on both static and neuromorphic datasets. To align the input dimension with the model, we added a reduction layer to the first layer of the model for conducting experiments on neuromorphic datasets. Our model achieved better performance compared to directly trained models, while the required time steps can be further reduced by using more advanced ANN to SNN conversion schemes. The RSM method reduces redundant spike operations while keeping model performance over a certain range of mask rates across various model architectures. For instance, the RSM method reduces MST model power by 26.8% at a 75% mask rate with no performance drop. According to the attention map, the models with varying mask rates focus on similar object regions at the same time step, as shown by the red outlines. In summary, applying the self-attention mechanism with ANN to SNN conversion narrows the performance gap between ANNs and SNNs. Besides, our RSM method can reduce power consumption by randomly pruning input spikes. Further work could optimize masking policies to expand the acceptable range without compromising performance. Applying RSM during SNN training could further optimize energy use, bringing SNNs closer to real-world deployment. Thanks for listening. You can visit our GitHub page for more information.